First zone.
All right, our second presenter this evening is Lee Whitcomb, Principal Engineer, also from Imagine Communications. And his bio reads as follows. Lee Whitcomb is Principal Engineer for Imagine Communications, the ABB Group, having joined in 1991. He received a bachelor's degree in computer engineering from the University of Waterloo and a master's degree in electrical and computer engineering from the U of T. He participates in SMPTE standards committees and with the Video Services Forum, including active membership on SMPTE 32NF Video over IP Ad Hoc Group, SMPTE 2022 Family of Standards, and the SMPTE 32NF Time Labeling and Synchronization Committee. He's also a manager on the Toronto section, and his professional affiliations include SMPTE, IEEE, and PEO. Please welcome Lee.
Okay, good. Can you hear me there? Is the mic on?
Yep.
Okay, so just out of curiosity, how many people feel comfortable with video over IP? Any experts out there? Oh, that's good. Okay, how about in terms of the SMPTE 2022 standard? Everyone has some familiarity with that? Okay, I did a talk a couple months ago. Were you all asleep? Okay, so today I'm going to talk about achieving error-free media or sort of video and IP networks. So just focusing on how we can use John's stuff here. We got video moving around the network, but we want to make sure that it's error-free. Okay, so I'm going to talk a little bit about network impairments, do a quick review of the 2022 standard, which obviously we need to do, and then get into the techniques how to achieve this error-free. So just looking at some differences here between SDI and IP. In SDI, we sort of have random bit errors. Normally these are quite small, so we get an error here, an error there. We use our EDH and CRC checks. We have our cliff effect that we're all familiar with. When our keel gets too long, things get bad. But in terms of errors, one signal doesn't impact another. The signal performance doesn't really vary over time. And the delay doesn't vary over time. So once I've commissioned my system, I've tested everything, it's all good, it pretty much stays good. Unfortunately, with IP, it's not quite that simple. So what are some of the sources of our errors? So we have our bit errors like we did before. So on our link, we can have a random error like we do in SDI. But we have other sources of errors. As we go into the switches can have congestion. This is going to cause problems. And we can have failure of our equipment and our links and stuff, which makes a little bit like SDI. So what are some of the impacts of these impairments? So our bit errors are going to cause packet loss. So before we just lost a couple bits, now when we have some bit errors, we're going to lose whole packets. When we get congestion in our switches, we're going to get bursts of losses. So not only are we going to lose one packet, we're going to lose a whole bunch of packets. Also, with the congestion in our switches, we're going to get packet delay variation, which is sort of jitter and wander. So this is our signals that the arrival time is going to vary. And unlike in SDI, we talk about jitter, which is very small numbers. These are like can be milliseconds, like big numbers. This can cause buffer underflows and overflows in our receiving devices, which is always going to cause a whole bunch of errors. And we're going to have one signal is going to start to impact another signal, where if my switch, I start up another video stream, my switch becomes congested, all of a sudden my video that was error-free is now going to start to have errors and stuff. So my performance can vary over time. So just because I've commissioned my system and everything's good, things can vary. Oh, also to say, if this is sort of interactive, so if anyone's got any questions, feel free to just sort of stop me as we go. We don't have to wait to the end or anything. Okay, so just looking at sort of visually what is the impact of an error. So can anyone point out in the first image here, there's a single bit error. Can someone find the error for me? The one black pixel in there? It's kind of up there. So in SDI, the odd little bit error, you don't really see it. I mean, if you hit EDH or something, or it's a TRSID, it may be a bit bigger, but it's quite small. Once we move to 2022-6, so this is uncompressed video, single bit error caused the whole packet to be lost, just about a half a line. So here we get our black stripe in the middle. So a single bit error, quite a lot more noticeable. And in the last case, 2022-2, so this is compressed video. So a single bit error takes out one whole packet. One packet could be 7 transport packets, and depending on which packets you hit there, could be something much more noticeable. So kind of the question of why do we care, why do we want to spend more on error protection than we did before, the effect of a bit error is now much more significant. Okay, so that's it on sort of just a quick review on some impairments. So the 2022 family, just a quick little review here. So we have a couple of older standards here. We have our 2022-12, which is for compressed video. So these have been around for a while, 2007. We have our newer versions, which are our -5 and -6. So this deals with uncompressed video. So these came out in 2012 and 13, so a fair bit newer. And then we have the newest member of the family, the -7, the seamless protection, which we'll get into in a minute. So all these standards, they basically deal with how do we take our video stream, how do we break it into chunks and into sort of packets, and then we're going to add these different headers. We're going to add RTP and UDP and IP headers on it, so we can sort of help us wrap up the video and allow us to route it and so on. Okay, so that was the really brief review of that. Okay, so now getting into the meat and potatoes as we get into actually the techniques you can use. So there's no one solution which is perfect for all applications. So you need to sort of think about what your application is and what you want to do. So some questions to ask yourself. So what are my system requirements? What kind of error rate am I trying to achieve? Am I trying to 99.9 or 99.9999? Or is this a Super Bowl? Or is this the, I don't know, some late night shopping channel feed or something? So what kind of error rate? We had the question about latency. So what kind of latency can I tolerate? Because different solutions here will have quite different latency impacts. So how much latency can I tolerate? What are my network parameters? What kind of bit error rates am I expecting? What kind of burst error rates am I expecting? What's the cost of bandwidth? Different solutions we'll see have different amounts of bandwidth. So how much does bandwidth cost you? Am I using software-defined networks that John was talking about? If I'm using software-defined networks, I can control congestion, I can make my network a bit friendlier, reduce my error rate, which may make a different solution better for me. So a few factors to think about. So achieving error-free, a few things I need to do. I need to be able to detect when my packets are corrupted. I need to detect when my packets get lost. And then I somehow have to regenerate my information that I lost. So in the case of detecting corruption, Ethernet and UDP had check fields. So I can see, is there a check field error? If there is, I basically throw away the packet. So packet corruption gets mapped to packet loss. I have RDP, so those different headers I was adding. RDP is a sequence number, so that helps me figure out which packet might be missing. Now we'll get into some like the cable industry stuff, some of they use just UDP and not RDP, and then that gets a little more tricky. And then the big one is how I regenerate this lost information. So the techniques I can use, I can do nothing. So this is what we do in baseband, and if my link is reasonably error-free and I want to keep my latency low, maybe this is an option. I can retransmit missing packets. I can use forward error correction. I can do path diversity, which is the seamless protection standard, or I can do time diversity. So these are some of the techniques we can do. Okay, so the first technique here, retransmit missing packets. So this is what we do in TCP. So when you're doing file transfers, this is what happens all the time. Now, for file transfer, this works well, but for video, not as good. So we just look at the top example here. So the sender is happily sending packets, so packet 1, packet 2, packet 3, and the receiver is receiving them, and it gets to packet 4, and for some reason packet 4 is missing. So now it has to talk to the transmitter, say, can you retransmit packet 4 for me? So eventually the transmitter transmits packet 4, the receiver gets it sometime in the distant future, and then once it's got enough packets, it can start generating its output stream. If we sort of compare that, we'll sort of jump to a second, but the forward error correction, with forward error correction, I'm going to insert special packets which allow me to regenerate the missing information. So in the case of the forward error correction, if I lose my packet 4, I have a fixed delay. It's not a variable amount. I know it's deterministic there. So then I can start my stream a bit earlier. Also, my amount of overhead is fixed. So unlike in the retransmission, it's a variable overhead, which can cause you some grief. And especially in the case of TCP, it's not as really, because of the lack of determinism, it's not good for video. Also requires here, sometimes here. So, but it's good. One thing that's good about it is I can have a very high error rate. I can be dropping a lot of packets, and I'll just do lots of retransmissions, and eventually my signal will get there. But once we get into, got to have that reverse channel to ask for the data. If I'm doing a multicast, so I've got lots of clients there, it's not going to work well. I've got this variable overhead. I've got this high latency. And in a lot of video solutions, they get into proprietary solutions, and that's not good. So this is sort of one option, but not a really good option. So we get into forward error correction. So within SMPTE, there's 2 standards that are relevant here. There's the 2022-1, which deals with compressed streams, and then the -5, which deals with uncompressed. And so a quick math lesson here. So you're thinking here, it's sort of at 8 o'clock on a Tuesday. I don't want to learn math. But anyway, we'll do just a really quick math lesson here. So this is an XOR arithmetic. So if I take the number, these are in hex, 7b XORed with 5d, XORed with 3a, XORed with 4c, I get the number 52. So I don't know if anyone's going to calculate, I want to check the math. Now there's a really neat property with XOR here. If I take the first 3 numbers or packets here, and I XOR with the last one, my 52, my extra number I created, through the magic of math, I get the number 4c, which, if you happen to look, matches the one piece of missing information. So using this very simple technique here, as long as I have 3 of the 4, I can regenerate the missing piece. So by transmitting this one extra piece of information, this extra 52 at the end, as long as I can receive 3 of the 4, I can actually regenerate the missing information. So that's kind of cool. I think it's kind of cool. So that's sort of the basis of what the SMPTE 2022 it uses. Now there are other techniques that do forward error correction that are more efficient, but they're more complicated. So this is what the 2022 decided. So we look at what SMPTE 2022 does is we take our packets, we make them into a matrix, and then we basically create, or we add these forward error correction packets, either row-based or column-based, or both. And it sort of comes down to, I'll get into the next slide here. And then we send these forward error correcting packets with a different UDP number, so the receiver can sort out which they are. So in terms of the recovery process, so if we imagine that the packets with X's are missing, so if we use our column-based column 1, we can recover that missing packet. In the case of, for all the other ones, we can recover it. Now, if we were just using the column-based, in the second column there, because we can only correct 2 errors, or we can only correct 1 error, that would then be non-recoverable. So this would be a case where the forward error correction could not do a recovery. Now also, if we included the rows, in this case, we could, if we do the right ordering, actually recover that error. This is where we also eventually break down from a burst error point of view, because if we have an entire row plus 1 extra column have errors, then we come to a state where it's non-recoverable. So we can cover some errors, but not all errors. And we have some different choices. We can decide the size of our matrix there, so we can control the number of rows and the number of columns. So by choosing different rows and columns, we affect the amount of overhead. So choosing different parameters will increase the amount of overhead. You can see here, some of the cases we got like 42% overhead, so we can add a lot of overhead. It also impacts our latency. The receiver has to wait for the entire matrix to be received, and so by the larger your matrix, the more your latency is. And it also affects how many errors can be recovered, and what's the longest burst error. So based on your system and your error rates and stuff, you're going to choose, and your latency, you're going to choose the best DNL that works for your system. And if you're dealing with SD, there's certain limits. If you're dealing with HD, so with SD, L times D has to be less than 1500. If it's HD, it can be up to 3000. And if it's 3G, the number can be 6,000. So there are bounds on how big these matrices can be. So you're adding overhead, you're adding some latency, and there's a certain amount of recovery you can do. And you're also adding complexity. So this solution is more complex, so the designs are going to be a little bit more expensive. But compared to the other solution, it works with multicast, which is pretty useful. You don't have to have a channel back from the receiver to the transmitter, so that's pretty useful. It's deterministic overhead, and it's also in the standards, which gives you good interoperability. So if you're deploying systems like this, some troubleshooting chips you may keep in mind. So with your Ethernet cables, you don't want to run them right at the length because you still have the cliff effect, so you want to back it a bit so you keep your error rate down. Your switches, you don't want to operate at capacity because then you'll get into congestion if you're running the switches too hard or too close to their capacity. So as you get congestion, you're going to get more of those errors. You can monitor your corrected error rates. That gives you sort of a sense of, as your corrected error rates are going up, your system is getting close to failing. You want to keep in mind maybe think about the video bandwidth, but remember as you add the overhead, what your total bandwidth is, so you might be exceeding what your link capacity is. Okay, so the next technique is path diversity. So this is a mouthful here. So we have the SMPTE 2022-7 seamless protection switching of SMPTE 2022 IP datagrams. So a bit of a mouthful. But basically what this comes down to is I'm just going to send the same information down two different paths. So as John talked about in that there we had switch A and switch B, I'm just going to send one copy one way, one copy the other way, and the receiver is going to put them together. And then the receiver has to be smart enough because it's now, for the most part, going to receive two copies of each packet. It has to know to throw away one of the packets. Okay. So there's going to be a quiz at the end on this, so remember this carefully here. So the key thing in the seamless switching is, from a high level point of view, what I need to make sure is that in my receiving buffer, so the packets are going to have some instantaneous latency to get into the receiver. The receiver at some point is going to wait until its buffer gets to a certain depth, and then it's going to start creating the output. And the key thing is for the seamless protection is it has to make sure that it has one copy of the packet from each of the two paths. And as long as it's got a copy of the packet from the two paths, then if one packet is lost or corrupted, then it can still use the other copy and you've got protection going on. Where you can, if your latencies aren't right and your buffers aren't right, you get into a situation where the packets from one path are either underflowing or overflowing the buffer, in which case you've only got packets from one path coming in. So in that case, you still have a signal, but you lost your protection. Because if you ever lose one of those packets, you're going to see an error on the outside. So if you're reading through the standard, you've got this busy drawing here. And basically, it's just sort of going over, so P1 and P2 are the instantaneous path delays from the two paths, and for the system to work, you've got to make sure that you've got packets from both sides. So you've got some of the important factors there. You've got the MD, the maximum differential between the PT and the PA. The PA is the earliest that a packet can arrive and still guarantee the seamless protection. The PD is the path differential, which is sort of a very important parameter. So the absolute latency is not a critical thing, but it's the path differential between your two paths. That's what sort of makes or breaks this. So as you're designing your system, you need to sort of think about what are the path delays, and as you're programming out the buffers in the receiver, you sort of need to keep in mind this. So anyway, just give you a bit of a primer there when you try to read through the standard there. So one thing we do in the -7 standard is we break out a few different sort of cases and stuff to come up with, to make it sort of easier on manufacturers to come up with reasonable buffer models. So we've defined 3 classes. So there's class A, which is sort of your low skew, and the example is sort of within a facility. And so we have these things as SBR, which is slow bit rate, which are really for compressed streams for your SMPTE-1-2. HBR, your high bit rate. So these are more than 270, or basically you're uncompressed. So in the standard, there's a single bit rate. So class A, it says that the path differential between your two paths needs to be less than 10 milliseconds. And then you have your moderate skew, which is for short links, where you can now have delays up to 50 milliseconds. And then there's this last class, which is for kind of either for super long haul or for rather specialized applications, and those can have very large delays. But then this means that the products have to have very, very large buffers. So what are your advantages and disadvantages here? So you've got 2 paths now, you've got twice the bandwidth, so some negatives. On the advantage, you can now have one complete path. You can have like one path have huge errors, and you still have no errors in your signal. Supports multicast like with forward error corrections, that's good. No reverse channels, that's good. Deterministic, and again, so with standards, so you have interoperability. So you're doing some debugging. If maybe this isn't working, what are some things to watch out for? So are your paths really diverse? So you think you're sending paths here and paths here, and maybe you're not using John's SDN, you're just letting the network do its own thing, and it happens that all the packets are coming to a common link and going down. And then if that link gets cut, then you lose both paths together. So just you want to make sure that your paths are truly diverse. You can monitor the buffer depths. So in that buffer model there, you want to be able to looking at those parameters. In your switches, there's lots of stats that if you use some of the back-end access, you can learn a lot about packet statistics, how much is being dropped, and so on. So lots of different things you can do there. So a slight variant is doing time diversity. So with path diversity, we're taking one packet, we're making 2 copies of it, and we're sending it 2 different ways. With time diversity, we're using one link, but we're still doing 2 copies of our packets. So we're taking one packet, we're sending it off, we're taking the next packet, we're going to wait a while, and then we're going to send it down the same path. So in that picture there, so we just need the one path. And this could take advantage of, say, if you know that in the middle of the network is, say, a SONET network, and it has a guaranteed 50 or 60 millisecond switching if there's an error, as long as your packets are not far apart, or if there's congestion in the switch, you can sort of hope that the second packet, the congestion will have cleared out by the time the second packet arrives. So still using the same thing, the receiver has to deal with getting 2 copies of each packet, but now you have them time shifted. So you still have 2 times the bandwidth, same thing. You're now dealing with higher latency because now you're intentionally skewing the packets, so you're dealing with much higher latency. But it has most of the same other advantages as the path diversity. Okay, so if you want to achieve your error-free in your IP networks, you need to think about this. You need to do some system design up front. You need to think about the parameters of your system. You need to choose a solution that makes sense for you. If you want to keep your bandwidth bandwidth is a bigger issue for you, forward error correction would have lower bandwidth. So using the SMPTE -1 and -5. If you want to keep your latency down or be able to handle more errors, you could use the path diversity, so the -7. You want to keep things which are to have high interoperability, so you want to keep the solutions which are standards-based. SDN is one of the things you can do to help control your network, keep congestion down. And with this, you need lots of new skills. I mean, you've got networking you're dealing with, you've got the new SMPTE 2022 standards, so there's a lot of new skills that you have to pick up. In the networking case, there's lots of good resources and courses and stuff. And that is it. Any questions?
I have a question, Lee.
Yep.
The -7 feature set that you spoke of, are there any requirements or restrictions with regard to the components that make up each of the paths? Can I just call my transport provider and say, yeah, I need a garden variety transparent land circuit, or do I have to specify I'm going to be using this for multicast traffic?
Yeah, okay, so basically the question is, do I need anything special in my lanes? And the answer is no.
Just any sort of commodity I can farm this quote out to anybody I want?
Yeah, I mean, from the standards point of view, from the transmitter's point of view, it's creating 2 copies of everything, and there's some rules on how I do that. And the receiver just has to know that I'm getting 2 copies of everything.
So the transmitter and receiver are unique.
Are unique, and that's what the standard really defines. The links of how you get there, that's purely up to you.
Thanks.
Okay. Any other questions? Or are we getting late? Okay. Oh.
So, in listening to all this, what it sounds to me is that both these projects really have the same common objective, which is to impose circuit switch network characteristics on a packet network. Is that a fair assessment of what's happening here?
Yeah, well, not as much from the stuff that I'm covering, not as much. But I mean, definitely the stuff where John's covering, and that's where.
Although I would say it the other way. We're using packet switch networks because they have good cost and good performance and so forth. And in the case of 2022-6 in particular, we really are using it to emulate a pure, to emulate SDI, including being able to regenerate SDI time. But I think that's a transitional scenario. By a couple of years from now, insert your favorite small integer there, it could be 2, it could be 20. We'll be in a zone where you have this computer putting out video through a packet switch network going to something else that looks a lot like a computer. Neither end really cares that it met the 0.012 parts per billion wander spec of SDI. They just care, did I get all the pixels of the frame because I didn't need them. So over time, the place where you have to meet the characteristics of SDI is when you're turning it back into SDI. The less we do that, the less we're going to have to worry about it.
Okay.
All right, Nick, thanks very much. I don't see Paul, so I suppose, unless there's any other business from the board, I'll move that we close the meeting with a stern reminder. We have the end of year barbecue, June the 10th, and boot camp, the 11th and 12th. The early bird registration closes Monday the 22nd, if I'm not, sorry, Tuesday the 22nd.
Next Wednesday.
Wednesday the 23rd. Did I get it right? Okay. Thanks very much for coming out, everyone. Have a great evening.